Good morning, students. So we'll move on to the next topic, that is symbol defining statements. Okay. So in previous session and all, we were discussing about relocation of program and all, right? Okay. Then literals we discussed. Then we need to go for one more machine independent. Okay, machine independent feature of assembler, that is symbol defining statements. Okay, the name only indicates the operands or the labels, whatever we are using in our program. Okay, that will be as usual normal. Okay, but sometimes if you want to, like how we are defining the symbol up to now. Okay, like if you want to use any particular label or any particular symbol, user-defined symbol, okay, then we need to define in some location, okay, with respect to their equivalent address, okay. So whatever the value we are residing with inside that address, that will be the value of that particular symbol exact. Is it right? Okay, but there we need to define the symbol first, then later we need to assign the address of that. Okay, later we need to read the value of that. So it will be a bit hectic exactly. Okay, but in today's session, we'll be discussing about two different varieties. Okay, how we can define such type of symbol with their appropriate value instantly. Okay, so those two equivalent or those two directives are equal. Okay, one is what EQU statement, and second is what origin we are calling it as. Okay, so these are the symbol defining statements. So we'll see how the equal statement or EQU statement used to work. Okay, we'll call it as equate. Okay, most assembler provides an assembler directive that allows the programmer to define symbols and specify their value as usual. Okay, like we are having such flexibility, like whatever the operands we are like familiar with, or whatever we are operand we are comfortable with. Okay, those operands we will be defining. Okay, along with their address and some value exactly. Okay, so that will be allowed by the each and every assembler. The directive used for this is EQU. Okay, the general form of this statement is, okay, just observe. First, you'll be having a symbol name. Okay. Later, it will be followed by a directive called as EQU. Okay. Means this symbol is equal to such value. Okay. Just observe. These are the three components of this particular definition. Symbol name will be equal to what particular value, that value should be available. Okay. If you are defining in such a way that, okay, then no need to go for any particular memory location for finding what is the value of this particular symbol or what is the address of this particular symbol. Name we have, value we are having. So in future, whenever you will be using this kind of a symbol, okay, we'll be referring with respect to value exact. Okay, we'll see that how it will be like that using the pass one and pass two will for the sessions. Okay, so this statement defines the given symbol, okay, that is entered in the symbol table, and assigning to it the value specified. The value can be a constant or an expression involving constants, okay, and any other symbol which is already defined. Okay, this is very important. So this is the only one restriction we are having. So if you want to assign any other symbol as a value for one symbol, okay, then that the value symbol should be already defined exactly. See, if you are trying to make B is equal to A, okay, then A must be defined in previous session, okay, or somewhere it should be already defined what exactly A, okay, then only we can. So what should be the value? Okay, symbol name can be anything, okay, you can name or you can give by your name also, doesn't matter, okay. But you have a restriction for the value. Value should be what? Sometimes constant or else an expression, okay, or else an expression which should generate a constant value. Yeah, which should generate a constant value or else a symbol, okay, which is already defined. Okay, one common usage is to define symbolic names, okay, that can be used to improve readability in place of numerical value. Okay, see here we are having one condition. Okay, like we are trying to load the registered T with 4096. Remember, this 4096 is the maximum value we can provide for any particular length exactly, or any particular register exactly. Okay, so here we have a description. See, this loads the register T with immediate value 4096. This doesn't clearly what exactly this value indicates. Okay, if a statement is included as, okay, so now see hash 4096. So this is the maximum length what we can transfer for one particular register. Okay, so here load T with 4096. Okay, what exactly this 4096 stand for? We don't know. Okay, but instead of that, what we can do over here is this 4096 will be made equal to some symbol. Okay, so if you read that particular symbol name, you should get some information. Okay, see, it is not useful for the assembler, I tell you. Okay, it is not at all useful for the assembler. See, assembler is working simple or working as usual. Okay, if you are writing the statement like plus load T with hash 4096, okay, the execution procedure will be same. If you are writing this also, execution procedure will be same exactly. Okay, see, compared to this here, two more lines are there. Okay, so milliseconds will be taken for executing this complete program will be more compared to this. Okay, immediate addressing mode you are using over here, but here you are using some direct use example. But okay, but for understanding the problem, if you are facing some situation like you need to identify some logical error and all, okay, that time if you find these kind of a numerical value, then you will be not able to understand what exactly these values are. Yeah, so that what we are doing over here is this 4096 will be made equal to some symbols here, maximum length. What is this 4096? I told you, right? This is the maximum value we can transfer for the register T exactly. So we are using a symbol name called as max length. Okay, see here, max length. If we read this max length, it states at maximum length. Okay, maximum length of what? Something. Okay, maximum length of something exactly. Okay, so now, what is it? Sorry. So maximum length equals 4096. Okay, so now maximum length means what? 4096. So no need to go for any particular memory location where exactly this max length is stored. What is the address of this max length? Okay, it doesn't matter exactly. Okay, so in next slide we'll be discussing like if this such type of instruction get executed. Okay, then how the symbol table or how the assembler will be executing this regarding the principle. Okay, then later just observe hash plus load register T with hash max length. Then also we are uploading the value of 4096 to the register T exactly. Same thing. Okay, but it will help the programmer to understand it properly. That's it. Then it clearly indicates that the value of max length is some maximum length value. Okay, when the assembler encounters EQU statement, it enters the symbol max length along with its value into the symbol table. See, whenever we use these kind of a direct use, right, equals and up. So before that, whatever the symbol name we are having, and after that equals whatever the value we are having, both will be uploaded to the symbol table. Remember this. Okay, during load register T, the assembler search the symbol table for its entry and its equivalent value as the operand in the instruction. Okay, how the operand we are finding in the symbol table, right? In the same way, it will be searching the symbol table. The object code generated is same for both the option discussed. Okay, but is easier to understand. See, the object code, whatever you are generating, right? Okay, for plus load T hash 4096 and load T, okay, with maximum hash maximum length. Okay, so if you are generating the object code for these two, then the object code will be same. Okay, object code will be exactly same, but it will be benefited by the programmer. That's it. Okay. If the maximum length is changed from 4096 to 1024, okay, see, this is also one of the application. Okay, now the maximum length you want to change from 4096 to 1024 exactly. Okay, it is difficult to change if it is mentioned as an immediate value wherever required in the instruction. See, feel that this maximum length, okay, or else the 4096, okay, is specified in 10 different locations of a program. Okay, 10 different locations of a program. We are specifying like plus LT with some register, load the register with this hash 4096. Then everywhere, if you want to change it to 1024, then 10 times you need to edit the program, right? But in case of if you are defining 4096 as equal to maximum length, then in one place itself you need to change maximum length equal to 1024. Then everywhere in 1000 location if it is available also, everywhere maximum length will be considered as a 1024 itself. It will make this editing simple exactly. Okay. Okay, we have to scan the whole program and make changes wherever 4096 is used. Okay, it is mentioned in, sorry, if we mention this value in the instruction to a symbol definition by equals, okay, we may not have to search the whole program, but change only the value of maximum length in the EQU statement only once. Okay, so that is the advantage, okay, of using this type of symbols exactly, or else direct use exactly. Other common usage of EQU statement is the is for defining values for the general purpose register. The assembler can use the mnemonics for register usage. Okay, like a register A, comma, X, index register, and so on. Okay, see here, some instruction, okay, expects the name of the register, some instruction expects the numerical representation of the registers exactly. Okay, so if you want to assign numerical value for such type of a register also, we can go for using this EQ statement. So here you have an example. We have, according to this, we are having two registers, accumulator and the X index register. So instead of using A and X, I would like to use the numerical value in place of this exactly. Okay. So A equals to what? 0 and X equal to 1. Okay. Then if you want to perform any arithmetic operation over these two or any kind of operation, instead of AX, okay, I can use 1 comma 0 or 0 comma 1. Such options. See here, okay, 0 comma 1 we are having, right? 0 represents A and 1 represents X exactly. Okay. So this will help us. Okay. So here, this statement will cause the symbol A comma X comma L to be entered into a symbol table with their respective value and into and instructions, okay, RMO A comma X would then be allowed. Okay, as another usage. Okay, so apart from this, we have one more usage, like we are having some general purpose register like R1 comma R2 comma R3 such. But for our program, instead of using those R1, R2, R3, okay, so we would like to use them with some other names exactly. Okay, like R1 register, I want to use it as a base register. R2 register, I want to use as an index register, and R3 register, I want to use it as a count exactly. Okay, so like if I use R1, R2, R3 for this procedure, okay, then I may be confused. Like R1 is for what exactly, R2 is for what exactly, R3 is for what exactly. Instead of that, what we can do over here is we can make those registers equal to their equivalent name for what purpose we are using. Okay, see if R1 is used for hacking the system, okay, hack S or hacksys, we can use it, right? Okay, then hacksys wherever we are using, that indicates what? R1, right? Okay, then any other such type of examples. Okay, so it depends on for what purpose you are using those registers. According to their purpose, we can give the name over here. So here, see, base we are using or base we are calling it as base equals to what? R1. So wherever if you are using a base, it indicates that R1 exactly. Index we are having, index is equal to R2. So wherever you are using, wherever you are trying to use R2, then you can use a word called as an index. Then it will be acting like an index register exactly. Okay, we can utilize that. We should use the such kind of a logic. Then count it is. So these were the few benefits of using equals exactly. So here we are having some condition. Just observe. See here, beta equals to alpha we are defining. Okay, but what is alpha? Alpha is defined in the next line exactly. Alpha reserve word 1 exactly. So this will create an error. Okay, so this should be swapped exactly. Alpha reserve 1. Okay, then later beta equals to alpha, then it will not generate any kind of an error exactly. Okay. Then one more statement we are having, that is ORG statement. Okay, so this will just redirect our pointer. Okay, that location pointer wherever it is. If you are using this ORG statement with some value, okay, then that location counter will be reset to this particular value, etc. Origin means wherever you may be available, just come to this particular location. What is that location? The value which is specified over there. Okay, fine. We'll go through this. So this directive can be used to indirectly assign value to the symbols. Okay, the directive is usually called ORG. Okay, or ORG for origin. Okay, its general format is ORG value. Okay, where value is a constant or an expression involving constant and previously defined symbols. So here also we can use such type of logic for the value. Okay, when this statement is encountered during the assembly of a program, the assembler resets its location counter LOC CPR, okay, to the specified value, okay, wherever it may be. Or it may be executing a instruction which is located at a byte number 1000. Okay, ORG 0 if it is there, then that 1000 will be reset to 0 exactly. Okay, from here, okay, we can start assigning some value. Okay, indirectly exactly. Okay, it is not direct. So what we are trying to do is using origin, we are bringing our location counter to some X value. Okay, from that X value, we are starting assigning the values for some X symbols exactly, some other symbols exactly. We'll see that. Okay, how we can do this. Since the value of the symbol used as labels are taken from location counter. Okay, the origin statement will often, sorry, okay, origin statement will affect the value of all labels defined until the next org is encountered. See, when we are changing the location counter value from the original value to origin value, okay. So from here up to the next origin statement, so in between, okay, whatever the statements we are defining, so those values will be affected exactly. Origin is used to control assignment storage in the object program. Okay, sometimes alternative value may result in incorrect assembly exactly. So it's also one of the problems we are facing. Okay, let it be, but we are not using it much. Okay, sometimes we may be using this origin statement. Okay, so it is tolerable, no issue. Then org can be used in label defining. Okay, suppose we need to define a symbol table with the following structure. Just observe it. So this is the symbol table. The symbol will be in first column, value will be in second column, and flags will be in the third column. So the task is what total 100 different entries we need to provide, means 100 different rows. Okay. So for managing the symbols here, 6 bytes are expected, means 2 words are expected exactly. For managing the value, we need 1 word, okay, 3 bytes. For managing the flags, we need total 2 bytes exactly. See here, 6 plus 3 plus 2, 11 exactly. Total 100 entries are there. Total 1100 bytes should be reserved. Is it correct? 1100 bytes should be reserved exactly. Okay, so this is what the expectation, okay, of our symbol table. So we'll see that, okay, how we can deal with this using the ORG statement. This symbol field contains a 6-byte user-defined symbol. Okay, value is a 1-word representation of the value assigned to the symbol. Flag is a 2-byte field specifies symbol table and other information. Okay, fine. The space for the table, okay, that can be reserved by the statement. Okay, sim tab or s tab reserved by how many? 1100 exactly. So we are reserving this 1100. Okay. Now, if you want to refer, okay, if you want to refer to the entries of the table using index addressing, okay, place the offset value of a desired entry, okay, from the beginning of the table in the index register to refer the to refer to the fields, okay, symbol value and flags individually. Okay, we need to assign the value first as shown below. Okay, fine. See, symbol is equal to what? Syntab. Is it right? Syntab means what? The beginning. Okay, syntab means what? The beginning address. Then the value, okay, if you are trying to access this particular value, just observe, value is equal to syntab means the beginning address of the syntab plus 6. Why? Because symbol, the first one, whatever the symbol we are having, that is acquiring total 6 bytes. So syntab plus X exactly. Then here we are having flag, okay, equals to what? Syntab or S tab plus 9 exactly. Because 6 from symbol, 3 from value, then later whatever the bytes we are having, right? Okay, that will be for flag segment. So this is how we are utilizing the equals right now. We are not yet done with the origin exactly. Okay, fine. So now just observe this. To retrieve the value field from the table indirect by register X. Indicated by register X, because the field bar is studying over there. Indicated by register X. Okay, we can write a statement. Load A with value comma X. Okay, see here, the whatever the value you are retrieving. Okay, how it should be done. See, load accumulator A. Okay, what we are trying to access, we are trying to access the value, particular value. Okay, comma X. Okay, means X is the index exactly. X is the index exactly. Okay, means if you are trying to access the value, then X will be 0. If you are trying to access the flag field, then X should be 2 exactly. It should be 2 exactly. Then value plus 2 will be indicating for flag. Okay, the same thing can be also done using the origin statement in the following ways. Okay, first what we are doing here, symbol table, how many bytes we are reserving? The total 1100 bytes we are reserving. Then origin to S tab. Okay, so wherever, if it is at 2000 location also, your location pointer will be reset to syntab location. Okay, syntab location. Here we are trying to reserve something. See a symbol reserve 6 byte, value reserve word 1 byte. Okay, flag reserve byte 2 exactly. Okay, from here, we are trying to observe it very carefully. We are trying to assign the values. Okay, we are trying to assign the values according to this origin, right? According to this origin address. Symbol means what? How many bytes we need to reserve? 6 bytes. So here, where you are pointing, right, from here, SIM tab, from here, SIM tab, we are reserving 6. Then later, from here, SIM tab, we are reserving 1 word after this. Then after that, we are reserving 2 exactly. Then later, org S tab plus 1100 means we are resetting this location. Okay, so what org we were setting it for the beginning of the SIM tab. After that, see how many bytes we were reserving? 1100 bytes we were reserving, right? Okay, like that, we are incrementing it how many times? 1100 times. Then we are out of this particular organization or original set. We are out of this original set. We are origin to some other value exactly. The first statement allocates 1000 bytes of memory assigned to label S tab. Okay, in the second statement, the origin statement initialize the location counter to the value of S tab. Now, the location counter points to S tab. The next 3 line assign appropriate memory storage to each of symbol, okay, value and flag symbol. The last origin statement reinitialize the location counter to a new value after skipping the required number of memory for the table S tab. That is S tab plus 1000 exactly. While using org, the symbol occurring in the statement should be predefined as is required in EQ statement. So here, the origin. So whatever we are using over here, that should be defined it first. Here also, right? Origin, S tab we are reserving. Okay. What is that S tab exactly? S tab we are reserving here total 1100 bytes exactly. So that restriction we have also for origin statement also. So this is for now, students. So these were the symbol defining statements. Okay, using which we can define some symbols instantly. Okay, so this is for now. So next session, we'll meet with next topic. Thank you, students.